Okay, this is for section 3-2, which is polarity of bonds and molecules. Alright, so before we can talk about bonds, polarity of bonds and molecules, we are going to talk about something that are called Lewis dot structures. Well, what's a Lewis dot structure? Okay, it's a model of how atoms are covalently bonded to make a molecule. Okay, so in order to do Lewis dot structures, we need the pieces, if you will, to make Lewis dot structures. And these are called Lewis dot symbols. Okay. All these do is they just show the valence electrons for an atom, for any particular element. But more importantly, not only does it just show how many valence electrons, but it shows where the half-filled orbitals are located. Because remember, those half-filled orbitals are crucial for creating the covalent bond, because that's the electron that it's going to share with another atom that also has one half-filled electron. So together they're going to share, and they're going to have shared ownership, if you will, of a pair of electrons. Now, because each family has a certain number of valence electrons, they all have the same Lewis dot symbol, if you will, the pattern. So I'm going to just simply pick a member of each of the different families as an example. So we're going to start with the alkali metals. Okay, and for that one I'm just going to do sodium, Na. Okay, and so you write the symbol for the element, and then we're just going to make one dot for each of the valence electrons. Okay, so I just decided to put this dot on top. Alright, now we'll go to the next family. That's the alkali earth. Okay, and from that family I'm going to pick magnesium. Now that family has two valence electrons, if you remember. So I'm going to do one dot here, and then I'm going to do one dot over here to this side. And each one of these is a valence electron. Alright, the next family is boron. Okay, and from the boron family I'm going to pick the element aluminum. And boron family has three valence electrons. So I do 1, 2, 3. Starting to see the pattern here? Okay, next we have the carbon family. And from the carbon family I'm going to choose the element silicon. Now the carbon family has 4 valence electrons, so I'm going to do 1, 2, 3, 4 valence electrons. Alright, now we're moving on to the nitrogen family. For the nitrogen family I'm going to pick the element phosphorus. Now these have 5. Now what does it look like? So you see it kind of looks like the elements have 4 sides that you could put valence electrons on. So here we're going to do 1, 2, 3, 4, and now I'm going to go around again, and this time we have a pair of electrons over here. Alright, the next family is the oxygen family, and I'm going to do the element sulfur. Remember, this family has 6, so just follow the same pattern. We're going to do 1, 2, 3, 4, 5, 6. You notice for the oxygen family, 2 sides have pairs and 2 sides have single dots. Alright, and then we have halogens. And for the halogen family, I'm just going to pick the element chlorine. Yeah, that's how I write Cl. We've got 7, so we do 1, 2, 3, 4, 5, 6, 7. And last, the noble gases. And I'll do argon, Ar. Remember, the noble gases have 8 valence electrons. They have nice filled both s and p orbitals. Okay, so these represent each of the family members. You just change the symbol in the middle for a different element from the same family. Now what's going to be really important is these single dots. And everyone, with the exception of the noble gases, has at least one single dot. These single dots are the half-filled orbitals. So these represent where that particular element is going to want to bond covalently with a different element. Okay, so let's talk about actually drawing the Lewis dot structure. Okay, so there's a few basic steps. Okay, one thing, you have to find there's a central atom. Central atoms, just like it sounds, it's the atom that goes in the center, and all of the other atoms that are part of the molecule will then attach to that central atom. Central atom usually appears at the beginning of the formula, okay, or has the most number of single dots, or carbon. Carbon has 4 single dots, remember, the carbon family? And so we find carbon as the central atom in a lot of molecules. If there's more than one carbon in your molecule, chances are pretty good those 2 carbons will be chained together, they'll be bonded together with all the other atoms stuck on them. Okay? That's how most of our very complicated molecules in our body, all the macromolecules you learn about in biology, are actually made of long chains of carbons with lots of other things attached to them. Something even DNA, all of the parts of the DNA molecule, from the phosphate backbone to the amino acids themselves, are all based on some string of carbon atoms that have other things attached to them. Okay, the second thing, okay, is that you're going to attach all of the other atoms to the central atom by lining up their single dots. And then you're literally going to draw a line from one single dot from another single dot to attach them. And then the last step you're going to do is you're going to look for leftover single dots. So after you've attached everything, are there any single dots that still haven't gotten attached to anything else? Okay. These are important because these show what are called double or triple bonds. In other words, this show where the 2 atoms are sharing 2 or 3 pairs instead of the normal 1. Of electrons. Okay, so we're going to do a couple of examples so you see how this particular thing works. We're going to start with the first one we're going to do is pH3. The name of this molecule is phosphorus trihydride. You'll learn how to name molecules later. This is a chemical formula. It's very important to note that a chemical formula has some important pieces in it. There are the symbols of the elements, and then there's numbers in the chemical formula. The numbers tell you how many atoms of the element are in the molecule. So, for example, this is P, this is phosphorus. There's no number. which means there's just one P. Okay, chemists are lazy, we don't write ones. If there's any other number than 1, we'll write the number. But ones we tend to just leave off. Okay, so this hydrogen, there's a 3 next to it. So that means there are 3 hydrogens and 1 phosphorus, all linked together. Okay, so the next thing we have to do is we have to find the central atom, and we have to draw the Lewis dot symbol. Now remember I said it's the one at the beginning, usually, it's P, or it's the one with the most single dots. Now hydrogen has the same pattern as all of the alkali metals, so it has 1 dot. So that's 1 single dot. Phosphorus, if you look back at the pattern for phosphorus, phosphorus has 5 valence electrons, means it has a pair, and then 3 single dots. So that's going to be our central atom. Alright, so I'm going to rewrite the P underneath here, and then I'm going to just simply draw the dots for P. Okay, so once I've done that, I go back to and say, okay, there's the P. Now I have to attach 3 H's. I look here and I'm like, there's 1, 2, 3 single dots. Those are the attachments for the 3 hydrogens. So I'm going to draw the symbol for hydrogen, which is H, and I'm going to line it up right next to the 3 single dots, because I have to attach them with drawing a line, so it makes sense that I'm going to draw them close by. Now I'm going to draw the hydrogen's valence electron in a different color. So hydrogen has 1 valence electron. Now I can draw this single dot for hydrogen any one of the 4 sides that I want. It makes sense that I'm going to draw it close to this single line because I'm going to connect these up. So for the hydrogen here, I'm going to do the single dot on top, and for the hydrogen here, I'm going to do the single dot to the right. Okay, and then I'm literally just going to connect them together. Do not forget this step. Okay, so now I have a little model, if you will, of phosphorus trihydride. Okay? This here on the phosphorus is the pair. You can't attach an atom here, except under very, very special circumstances I'll talk about in just a minute. Okay, so you see a pair, it means you have to leave it alone. You can't attach anything here. Alright, let's do another example. Let's look at oxygen molecules. Oxygens really, really like to be bonded, so much that they will bond to another oxygen atom if there's nothing else available. They would prefer to bond to something else. As we'll see, that's why oxygen is so reactive. Okay? It will break the bond with its little twin, if you will, and then go bond to something else. But if there's nothing else, it'll bond together, it'll be O2. So here's the question. Where's the central atom? Where, in this case, there really isn't one, because they're 2 identical atoms. So we're just going to draw those side by side and then bond them up together. Alright, so on this one, remember oxygen has 6 valence electrons, which means the pattern is 2 pairs and 2 singles. I'm going to draw this one. Now this one I'm not going to draw it exactly the same way, because it'd be kind of silly to have the single dots over here if I have to draw lines from these single dots to these single dots. I'm not going to draw them, like try to avoid that. So instead I'm going to put the pair out here and then the single dots so they're like facing each other. You can draw the pairs and the singles on any side of the symbol that you need to. So kind of think ahead. Okay, where am I going to have to connect them? It makes sense that single dots should be close to other single dots. Okay, so now I'm going to connect them together. So that's step 2. Now, for step 3, look, there's a leftover single dot. This O has a single dot, and this O has a single dot. Okay, you cannot leave any single dots without lines. So they're already sharing this pair. This means that they have to share 2 pairs. So this is 2 pairs of electrons that they're sharing. 2 atoms sharing 2 pairs of electrons. So this is an example of a double bond. Okay, our last example is C2H4. Okay, now where's the central atom? Well, at the beginning is the carbons. Now there's 2 carbons. Now we said that carbons like to bond to each other. Unlike oxygens that don't like to bond to each other unless there's nothing else around to bond with, Carbons like to bond with each other. So when you see carbons like that, okay, assume that the two carbons are going to chain together. Now carbon has 4 valence electrons, so do 1, 2, 3, 4. Okay, in this case I'm going to do both of them in the same color of dot. Okay, attach them together. Okay, now I'm going to go back and say what's left. 4 hydrogens. Now, if you have a molecule especially like that, and okay, the question is, well, there's 6 single dots, but 4 hydrogens. Where do I put them? In this case, try to make your molecule symmetrical, which means make one side of it look as close as you can to the other side of it. So I'm going to put an H on the left, and I'm going to put an H on the right, and I'm going to put an H on the top on this side and an H on the top on this side. That way the two sides look pretty identical. That's what we mean by symmetrical. Alright, so here's the dots for the hydrogens. Okay, I'll attach the carbons to the hydrogens. Okay, and what do we see? Yeah, we have a leftover. There's a single dot on this carbon and a single dot on this carbon. Okay, that means that we're going to have to connect these together, so in this case there's a double bond between the two carbons. Okay, so far so good? Alright, so now we're going to talk about the odd behavior of oxygen. Oxygen has a very unique ability in that it can steal a pair off a central atom, if there is one, to create the bond. Okay. Only oxygen has this particular ability. You can't do it with anything but oxygen, not even any other member of the oxygen family, only oxygen. Alright, so let's see what that looks like. We're going to draw the molecule. SO3. Alright, so here's our central atom, sulfur, right here at the beginning, because it's at the beginning, occurs one time, okay, and here is sulfur's Lewis dot symbol. Okay, now you go back and look at the molecule and you say, okay, I've got to attach 3 oxygens onto 1 sulfur. Well, you can see, wait a second, there's a problem because sulfur only has 2 single dots. So how's that supposed to work? Okay? And the oxygens are also going to have the exact same pattern. Each of them are going to want to attach to 2 other things. So it looks like we're really, really short on electrons. So if you see something like this, where it looks like you just don't have enough places to put the O's, take one O and bond it like you would normally think the O would bond. Okay? So let's just pretend for a moment there's just 1 oxygen. Okay. And so we'd attach it here, and we'd say, oh look, leftover electron, make a double bond. Okay. Well, that's really nice if our molecule is just SO. But where do the other 2 oxygens go? Well, this is where we have oxygen's strange ability. See, there's a pair here, sulfur, and there's another pair here on sulfur. So what oxygen is going to do, oxygen has the ability to actually steal this pair without giving one of its electrons to sulfur to share. So this is kind of like the friend, we talked about that sharing electrons. One of the analogies we used is that if you're standing in line with a friend and you want French fries and neither one of you have enough money, but you put your money together, and that way you can buy 1 package of French fries and you can share it. It's not quite the same as having your own share of package of fries, but it's better than nothing. Oxygen is the kind of friend that stands in line with you while you buy the French fries and then eats your fries and shares it. You're like, wait a second, you didn't help me pay for them. Okay? So we all probably know somebody like that. Alright, so this is what it looks like when oxygen does this pair stealing. You put the O right next to this. Now, rather than drawing the electron, the Lewis dot symbol for O this way, we're going to draw a little differently. We're going to end up with drawing it with like 3 pairs on 3 sides, and this side here is open because this is how it looks like when it's going to steal a pair. Okay, this is a single bond. This is no different than, hey, here's O's electron, here's S's electron, they're connected together. It doesn't really look any different in the molecule. Okay, and so this O is going to do exactly the same thing. Okay, so you can only draw O's Lewis dot symbol like this when O is going to do its pair stealing thing. So this is basically, this S is double bonded to O. This S is single bonded to this O. And this is how you create the SO3. So you can only do this with oxygen, because we see a lot of different molecules that have a lot of oxygens attached to the central atom. This is the only way it could get done. Alright, so now we're going to move on, and we're going to talk about polyatomic ions. Now you may ask yourself, what the heck is a polyatomic ion? Well, the word poly means many. So these are ions that are actually created by atoms that are covalently bonded to each other. But they usually don't have enough electrons for every atom in the group to fulfill the octet rule. That means that even though they're covalently bonded together, they're still short electrons. So they're going to have to behave like like an anion, and they're going to accept electrons, usually from a metal, to fill in the holes. And that's literally what we're going to do. So we're going to learn a little later, how do you name polyatomic ions? But right now, let's focus on what does a polyatomic ion look like? And how do I draw the Lewis dot structure for it? Okay, so this is what a polyatomic ion looks like. It looks like a regular molecule, except it has an oxidation number on it. Just like if you were drawing an ion for a metal or a non-metal. This is called nitrate. This is nitrogen. And the 3 oxygens, it's called nitrate. You'll learn about how to name them later. Alright, so first of all, we're going to start them exactly like any normal molecule. Have a central atom, and this is going to be the nitrogen. And so I'm going to draw the N. Okay, remember nitrogen has a pair and 3 single dots. Okay, now you say we've got 3 O's, we could put O, O, O here. The problem is if we do that, O, O, O here, remember each of the O's is going to have 2 and it's going to want to try to bond. So you kind of got a sneaking suspicion that you're going to have to see oxygen stealing a pair, which is the case. So remember when I said you do that, you could usually get 1 O on the normal way. So let's bond this O on the normal way. Okay, and so that O will make a double bond with N, and you say, okay, I know the O can steal a pair, and look, here's a pair right here on this nitrogen. So let's make the second O steal this pair off of the nitrogen. So I'm going to draw it, oxygen's Lewis dot symbol in pair stealing mode. Okay, totally cool. Now we got 2 of them on. Now here's the problem. We got 1 little electron, and if we try to put it on the normal way, we can't steal a pair because there isn't a pair there. We say, well, what do I do here? If I try to put it on the normal way, right here, okay, nitrogen's is in good shape. It has no single dots that are attached. But here's this 1 oxygen. It's missing 1 electron. Well, if you go back up here, the oxidation number here tells you how many additional electrons that this particular group is going to have to take from a metal to fill in any holes. It's 1. So this means there's going to be 1 extra electron. So I'm going to draw that extra electron right here, because if I could have another electron here, it would be like perfect. So I'm going to draw it, but not as a dot. I'm going to use the little E- symbol here. This is this electron here. So in other words, they get all bonded up, but they have to find a metal, and they have to take the electron from that metal to fill it right here to make all of the group members completely stable. So they're going to end up having a charge to them, which most molecules don't ever have a charge. So how do we show that this whole thing has a charge? Well, when we're all done drawing it, we're going to put a great big pair of square brackets, around it. And then we're going to copy down the oxidation number outside the bracket. So this means that this whole thing here is a polyatomic ion with a charge of -1. And here's why it's a -1, because it took an extra electron. So that's how you do polyatomic ions. You sometimes have to be a little bit creative and play with it a little bit. So I always suggest that when you do your little dot structures, you do them in pencil, so you can erase if you make a mistake.